Right. So my name is Cees van Wijk. I'm a blockchain specialist at ING, working primarily with Ethereum for almost 2 years now. I'm here together with my colleague, Coen Ramaekers, security architect and specialized in cryptography. We're going to tell you all about our zero-knowledge proof, but before that, just a brief 1 or 2 minutes, one slide of the things in general we do with Ethereum at ING. Basically, the work we do is we have 3 categories of work. We build applications on top of blockchain platforms, on top of Ethereum and Quorum as well. We compare the major platforms that are out there. So Ethereum, Quorum, Corda, and Hyperledger Fabric. We research them, see how they relate. If you look at the Corda, Fabric, and Quorum, they all provide confidentiality features. They all provide pluggable consensus, and it's very interesting for us to learn the differences between them and to see which platform should be used for which use case. And last but not least, the other category of activities is the research. We research different consensus algorithms, and we research crypto. And that's how we came up with the zero-knowledge proof implementation that we'll touch upon later on. There's one application that we've built that I would like to highlight in this member update. And that's the trade finance application. If you look at trade finance today, how it works, it's basically people sending paper documents all over the world, simply because it's the only way that we have enough trust, that a bank guarantee is really a bank guarantee, and that a bill of lading is trustworthy, and that goods really have been delivered to a ship. So far, in the past decades, there have been many initiatives to automate this, but before blockchain, all of these were proprietary and centralized. Many of them were basically document management systems. People scanning documents, storing them there, and then if there's some customs employee at some far end in the world, he needs to trust something stored in a database in Amsterdam, that doesn't really work. And that's where distributed ledger comes in very handy. So we had a successful pilot together with Société Générale earlier this year. And basically we learned that obviously it's much more efficient if you run it on the blockchain, but also we ran it on Ethereum. So like Jeremy said earlier, everybody agrees that there are several points which makes Ethereum not suitable for an enterprise usage, which 2 of them are the transaction throughput and the lack of confidentiality. So that's why we're now assessing Quorum. It's very easy if something runs on Ethereum. Basically it also runs on Quorum, and then you add on your privacy features. And so far the results look very promising. We see that the pluggable consensus, that's the thing we like most. So we're very pleased to hear that PBFT is also being worked on as one of the consensus algorithms for Quorum. Because for us as a bank to run a blockchain and to really get the benefits from it, we definitely need a Byzantine fault tolerant consensus algorithm. Crash failure tolerant for us is not sufficient. All right, that said, let's move on to the zero-knowledge proof. It's a bit slow.
It's so zero-knowledge we can't even see it.
Yeah, secret data is hidden. Somehow it's starting a bit slow, but no worries, we'll get there. What's going on? There we go. Right. So one of the projects we're working on right now is the zero-knowledge range proof in Ethereum. Matthew from Clearmatics earlier on told that there are several forms of zero-knowledge proofs. ring signatures you could regard as one of them. Digital signatures you could regard as another. You could say, I prove I have a private key that belongs to a public key, but I don't reveal the private key. What we're doing here is we're implementing a range proof. So basically, we are allowing the whole Ethereum network to prove that a secret number, to validate that a secret number lies within a known range. Why is this useful? Before we explain how it works, how we implemented it, let me explain why it's useful with an example. Say you're building a smart contract, and the nature of your content actually of the service, the application you're building, actually requires that it can only be used by adults. So you want to make sure that everybody who uses it is above 18 years old. Whether it's gambling or other 18+ rated content, let's say opening a mortgage, it's typically something kids don't do. And then in that case, you know the interval. The number, the age, should be between 18 and a very high number. The upper limit is not so relevant in this case. However, you don't want to reveal the actual age of the person that uses it. You don't want the whole blockchain to know somebody's age. So what you could do is, if there's a trusted oracle that provides an age, for instance, a government, an identity, a solution like Uport, or an employer, or another trusted source, it can provide a commitment. It can provide a commitment of your age or any other number. Then the end user can use that to create a range proof, to prove it's within a known range. And then the whole Ethereum network can validate the proof that is generated. The reason we built a precompiled contract for this is because the validation, it takes many computational steps. It also requires processing very large numbers, so it's not practical to do that on the EVM. So we created a precompiled contract so that from Solidity we can call the function outside the EVM and get the result back. I just mentioned an example of an age, a proof of age, but for instance it could be a salary. Say you want to rent an apartment and the owner of the apartment wants to have a proof that you earn at least £20,000 per year, something like that. Then your employer can provide a commitment on your salary. You create a range proof, the whole network validates, and nobody knows what you earn, but everybody knows it's more than 20,000. You could use it as a proof of location. A location is basically a number, two numbers. As you say, I'm in the UK, but you don't disclose where. Or, for instance, that a payment is within limits. So, how does that work? Cool.
All right, thanks, Kees. So, first of all, we'd like to explain what a zero-knowledge proof is. And I think everybody in the room now, thanks to Matthew, knows what it is. And we picked a different analogy, one that I heard that certain people in this room don't like. So, besides the analogy of the deck of cards, you can also have the analogy of a cave which has a secret door in somewhere in the cave, which requires a code to open. Alice claims to know the code to this door, and wants to convince Bob of the fact that she knows this code without actually showing him. So the way they can do this is Alice goes into the cave while Bob isn't looking. She picks either side A or B. When she's at the door, then Bob calls out which side of the cave she should exit, either A or B. And if Alice knows the code to the door, she can always complete this. Of course, if she's lucky and she entered the side of the cave that Bob calls out that she should exit with a 50% chance, she can come out without actually knowing the code to the door. But if they repeat this process a number of times, then the chance that Alice keeps choosing the right side of the cave to go into decreases by 50% every time. A zero-knowledge proof has three important properties, which are completeness, soundness, and zero-knowledge. Okay. So completeness means that if the statement is true, that Alice actually knows the code to the door, she can always convince Bob as long as both parties are honest. Soundness means that if the statement is not true, then she can, if she's dishonest, never convince Bob of the fact that she knows the code to the door. So if they do this process enough times, then eventually she will pick the wrong side and Bob will know that she's lying. And zero knowledge, which means that if the statement is true, then no dishonest verifier can learn anything about the secret besides the fact that the statement is true. Okay, so in this analogy we used here, this zero-knowledge proof is obviously interactive. Each time Alice goes in, Bob has to call out which exit she should exit. If we translate this into a distributed ledger setting, it's not very convenient for this zero-knowledge proof to be interactive. Especially if all the nodes are verifiers, you don't want all the nodes to present the prover with a challenge that she needs to use to prove that she actually knows the secret. So to solve this, you can make a zero-knowledge proof non-interactive by using something that's called the Fiat-Shamir heuristic. And this heuristic claims that you can replace the challenge with a hash function. And because this hash function is unpredictable and irreversible, it can be used to create a random challenge as if Bob were creating this random challenge for Alice to use in her verification. So as Cees mentioned, we are intending to use the commitment by a trusted third party. The way we intend to do this is that you generate the prerequisites of your zero-knowledge proof first, which is a time-consuming matter, and then you share the public values of these prerequisites with the trusted third party. The third party then certifies your public parameters that you will use in the zero-knowledge proof together with the commitment of what you are going to use in your zero-knowledge proof. So for instance, your birth date to prove that your age is between a certain limit. And since this commitment is fixed together with the public parameters of your zero-knowledge proof, it's impossible to use a different value than your actual birth date within the range proof. Now at a later stage, when you require this, you can use this range proof to prove that your birth, or you can use this commitment to prove that your age is actually within this range. And the upside of using this method is that the trusted third party doesn't have to be available at all times. Otherwise, you could just have the third party certify at your at the required time that you are indeed over 18 or whatever you want to prove. So the protocol is based on the paper that's called an efficient range proof scheme by Mr. Koen and Feng Bao. Unlike the ZK snarks that have been mentioned a couple of times already tonight, this is only used to prove a specific function, namely that your secret number is within a known range. The protocol relies on several building blocks. The first one is how to generate secret order groups. So we'll go into what the secret order principle is in a minute. The fact that using a secret order group is required for the zero-knowledge proof. And also there's two other zero-knowledge proofs that are used within the zero-knowledge proof, namely the proof that a committed number is a square. So we're hiding a number that is a square. And the proof that two commitments hide the same secret. Other properties that are used are the Fiat-Shamir heuristic, as mentioned. The discrete logarithm problem is one of the foundations of the security of the protocol. And together with that the integer factorization problem on which the secret order principle is based. So at first we had these 4 slides, and we wanted to explain in more depth how our zero knowledge proof works, but we thought, well, let's not do that. That might take a bit too long, and since we're the last talk, everybody wants to go and grab a beer. So we decided to just explain the 4 properties that we mentioned earlier. The first one is a discrete logarithm problem. Maybe you all know this, but in real numbers, taking the logarithm is as the inverse of a exponentiation is a trivial operation. But if we instead of the real numbers, we take a cyclic group, then calculating this discrete logarithm appears to be a very hard problem. So if we take b and x elements in the group G, and we take b to the power n equals x, then it's very hard for a given x and a given b to find what the integer n was. Many algorithms to solve this exist. Of course, you can try every exponent until you find out one that works, but none of them run in polynomial time. So that's why it's considered a hard problem. Unfortunately, there is an efficient quantum algorithm to solve this, so hopefully the quantum computers will not exist for quite some time. The next one is the Fiat-Shamir heuristic we mentioned earlier. We can relate this to the discrete logarithm problem. So if Alice wants to know that she actually knows the solution to this hard problem, she knows the exponent n for which it holds that b to the power n equals x. She can pick a random integer v and publish this s is b to the power v, and then compute a challenge based out of a hash function of the 3 earlier published values b, x, and s. And then she can compute r as a proof of the fact that she knows x, which is equal to v minus n times c. And anyone then can check that s indeed equals this b to the power x, x to the power c, and find out that Alice must have known this secret n, or she somehow knows how to correct the discrete logarithm problem. The next one, probably everybody knows over here, but we thought it was nice to include anyway. The integer factorization problem. So every integer can be factored into a product of its primes. If we have a look at 15, then everybody will immediately think, oh, it's 3 times 5. 1337 is a bit harder already, but also not too hard. You can make mistakes by including easy prime factors like the next one. But if we take the last one, which is the product of 2 very large primes, then we can imagine this is a very hard problem for anybody to solve. And also here, no algorithm that runs in polynomial time exists to solve this. But again, there is an efficient quantum algorithm to do it. The secret order principle is derived from that. In a cyclic group, every element has a order, which is the exponent that you require for this element to become the identity element. As an example, if we take the integers modulo 7, then we can find out that 3 has the order 6. But the secret order principle states that if we have a modulus that is the product of 2 primes, then because of the integer factorization problem, it's hard to find out what the order of an element in this group is, or what the multiple of an order of an element in this group is. So these are the foundations that the zero knowledge range proof relies on. Now Cees will continue by showing what we did with it.
Yeah, thanks Koen. So in order to use these building blocks that Koen just described, and in order to implement the white paper that Koen mentioned, we created a precompiled contract. So how that works is basically the call is the same from, I don't know who of you is familiar with writing Solidity code on the EVM. Can I see some hands maybe? Okay, yeah, that's good, roughly half. So this probably looks very familiar. You have a contract, in this case it's called ZKP range proof. It has a function, in this case open account, and you send some parameters to it. In this case a lower bound, upper bound, and an input. The input, that's the proof. So from here Basically, you don't see that there's a precompiled contract involved. But then if you look at how the Solidity, what it looks like, what it does when I call the open account with the lower bound, upper bound, and the proof, then you see I call the range proof validate with these parameters. Range proof, that's defined as an interface, which I instantiate on address number 5. Address number 5 I defined in my Geth client in contracts.go as the 5th precompiled contract. Ethereum, by specification, has 4 built-in precompiled contracts. EC Recover, SHA-256, and 2 others. On addresses 1 to 4, and we added a 5th one. And here you see also a difference. If you do a SHA-256 hash from Solidity, Solidity has a built-in function to do that. So you don't notice, as a programmer, that you're going to invoke a precompiled contract on address 2. But that's what happens under the bonnet. And that's what we do here explicitly. And that's also one of our next steps, to change Solidity to add a function instead of having to call, having to do the plumbing, writing an interface, and then calling it on this address. Then if you go, once you do this, then you enter our ZKP range proof function. It's a struct, it implements the required gas. You see that's a to-do for us. It says 0. So what we're going to do is we're going to benchmark our function against other Ethereum functions, and then we're going to calculate how much gas it should consume. It's important to get that right. If it's too low, it's a vulnerability. If it's too high, we're wasting people's ether. Then in this, the run method, you see it takes a byte array and it returns a byte array. So in order to make sense of that, we should skip the first 4 bytes, which is the hash of the method signature, then take it from there. So the first argument, the lower, it's the after the first 4, it's the next 32 bytes, which we convert into a big int. Then the next 32, it's the next argument, and the proof is everything after the 68th byte in the array. Then from there we call the function, and with the return value, which is a boolean, we convert back to a byte array of 32 long, where the last byte has to be set either to 1 if it's true, or to 0 if it's false. Then the range proof itself. It's a very long implementation. I don't want to show all of it, but basically, you see, it implements all the building blocks and the whole protocol that Coen explained. Where we are right now, the reason we call this a sneak preview is because where we are right now is we have this library in Go running, so we can generate proofs. We can validate them very efficiently. It either returns true or false. So that's the part that's working. We're now integrating it into Geth. We can call this function. Basically, we're decoding the byte array into all these parameters, and then it's up and running. So it's a matter of days rather than weeks. So that brings us to where we are right now. The next steps is integrated in Geth. Obviously, a lot of refactoring and cleaning up the code. Calculating the gas usage, you saw that it's still hard-coded to 0. It should be something sensible. Open source it, because of the nature of the work. We started small with a small group. It's a lot of research and exploratory work. But as soon as we have it up and running, then we want to leverage the expertise in the EEA community and in the broader Ethereum community. Then we're going to change the Solidity compiler to add a function to call this. So you don't need to bother about all the plumbing we have now, the interface at the address. Currently, we generate proofs in Java. That was the first implementation. But we want to also be able to have a library to generate the proofs in JavaScript, so it integrates well with Web3, which is popular. Implement a showcase. And we think it would make a lot of sense for both enterprise Ethereum and public Ethereum. There's only one way to find out if the Ethereum community agrees with that. So we'll start an Ethereum improvement process request. Are there any questions? Yes.
So in one of the primitives you're using is secret order groups, which is like composite order groups. So you're using like bilinear pairings there, right? And composite order groups have trapdoors in them, meaning like, does your scheme have this issue where if I like root or if I exploit the trusted third party, then I can unmask all commitments on the chain?
So we intend to have unique groups for every user of that. So I'm not sure how you would trapdoor then by exploiting a trusted third party to find out all commitments. So the commitment relies on which secret order group you're using, and that's unique per user. So. Okay, thanks.
Who defines the bounds for the contract? You have a lower bound and an upper bound. So if it was for age, if I as just a random user was to ask, is a particular person between the age of 18 and 20, and it returns 19, or yes, it is true, then it's obviously they're going to be 19. So how do you prevent people being clever or basically trying to ask questions over and over and over again until they eventually get statistically to an answer that the person was 19? How do you prevent that?
There's in this precompiled contract. There's nothing specifically to prevent that. It's that's more about how it's being used. That it should be sensibly used. And the range should be wide enough. It's like when you start hashing and you have a limited number of inputs, then it's also dangerous. But then it's the same with this. If the range is too small, then you can or you ask too many small ranges, then you can determine the actual value.
Anyone else?
I know you didn't benchmark it yet, but like, what's your estimated computational complexity for this? Like, if you had to pick a gas cost, what would you assume?
I know it's very fast. The reason I don't want to run it is because I can afterwards. We can have a look, and I'll show you. If I do a test, then it runs a couple of tests, a couple of validations within a second, including starting up the test and all the overhead. So that's the fast part. We'll have to get more precise figures to really come up with a gas number, but it's fast. But you saw when I started that it was slow with PowerPoint, and every time I do a page down, and it's very slow to come with. So there's something with the PC why I don't want to show it, but we can show it afterwards.
Also, the computationally hard stuff like generating your secret order group is done beforehand, so that doesn't rely on any gas usage as well.
Right.
That's it. Oh.
Which trusted third parties have you actually got on board at the moment? And where are you getting this trusted reference data from?
How we imagine it is, for instance, employers for identity attributes or for salaries, those kind of things, or third-party identity providers like Uport. Your question, who do we have on board? Nobody yet. It's in the early stages. Yeah.
How do you validate the information input is from that trusted third party?
Yeah, so with a digital signature.
Yeah, so the commitment is signed by the trusted third party with a verifiable signature. So.
Assuming you're speaking to the trusted third party.
Yeah, well, if the trusted third party has a publicly available certificate from a trusted CA, of course it's all a big of trust us, of course, but.
Maybe you could whitelist signatures too.
You could, sorry?
Whitelist signatures.
Yeah.
Whitelist,
Yeah,
yeah.
sure. Yeah. For instance.
Get something about ring signatures to talk about that.
Well, we can include that, of course.
Right?
Right. Thanks.
Well, thanks a lot.
Cees and Coen, thank you.